Welcome to part 4. It's page 771, and we're in the immune system, part 4, and we're going to be taking a look right now at interferon. Interferon is described right here. I'm first going to actually come right back here to this little handout in which we look at viral infections and the way to defeat them. It's possible to have a virus of a mild sort. It's been found that sometimes a mild virus will prevent a particular individual from contracting HIV. Usually that's one virus at a time, and it's because of interferon. What is interferon? Interferon is something that's released when a virus enters a cell and infects a cell in the nucleus and sort of intrudes into the DNA or the genome. That cell detects the, how shall I say, disturbance in the force and releases this molecule called interferon. It releases it to the uninfected cells, which then have receptors for interferon, and they produce a endonuclease, or that is to say an enzyme which digests incoming RNA, DNA types of viruses. So let's take a look at the at this particular presentation here. Here's the virus coming in. It does its little infection number. It inserts itself into the DNA of the host cell. Okay, so and then it's producing, replicating itself, and then this actually is an indication here. Here's the replication of the virus up here. This is instead, rather, it is a stimulus for the synthesis of interferon. Interferon is released, and you can see that it's binding to a receptor on a neighboring cell. The neighboring and as yet a naive cell is going to be activated in its genome to produce antiviral mRNA. Okay, and it could be anti-RNA or anti-DNA depending on what's being stimulated here. It's an endonuclease, so we're going to be going up against and cutting the sequences of lengths of nucleic acid, RNA or DNA, that appear in the cytoplasm. How do we know we're not interfering with our own RNA and DNA? Is that we actually have linker regions and lengths for the condensed DNA, and we also have methylation on our nucleic acids that are species specific, so we're not going to mess up our own RNA and DNA. Okay, so these are important details. When you have something that's not self, then this is able to work properly. Okay, a very potentially effective method is interferon. We press on over here now, and we're going to visit complement. My master's degree in immunology was taught to me, or presented or mentored by a PhD out of Stanford who was an expert in complement. That's what his postdoctoral work was in, Dr. Remo Morelli, who has since passed away, but was essentially my very, very favorite, although I like them all, one of my favorite mentors in graduate school. So this is sort of a la Stanford version, shall we say, or Remo Morelli version of the presentation here. We're going to follow the classic pathway. And basically these molecules, these complement molecules here that I'm numbering for you, C1, 2, 4, etc., are products of our liver. Okay, the biosynthetic pathway is in the liver, and these are dissolved, minding their own business. Here we have an immunoglobulin G. It could have been an immunoglobulin M. At any rate, we get activation of complement number 1. This is C1 right here, and it's going to be activated, C1A, because it's touched the complement activation site. C2 and C4 were previously minding their own business, dissolved in the blood, but because of activated C1, they joined up and created this molecule right here, this complex, that took C3 and cut it up into C3A and C3B. C3B initiates this long polymer right here, which is going to become an attack complex. Okay, here's C3B getting cut up. Here's C3A, which is going to become an anaphylactic molecule, and it's going to act in a particular area that we've already identified, and that area is right here. Okay, basically here we have the outflow of leukotrienes, and this is the anaphylactic side of the inflammatory system, and you can see it's being activated by C3A and C5A, the anaphylactic molecules of interest. Okay, so here we have C3A. C5A is also going to contribute to anaphylaxis, which is an enhanced inflammation, and it's at times thousands of times more powerful than ordinary histamine. So if you can imagine that, the death of a small child by a single bee sting can be that sort of intensity, anaphylactic shock. Okay, so then we have C3B initiating here. We also have C3B coming over and taking up residence on the surface of an infected cell, and it becomes the barbecue sauce for that cell, and it's going to attract neutrophils and macrophages and so on to that cell. So this is the salt lick, as it were, the attractive item here, the opsin, that attracts phagocytosis. So that's another additional item. Once we have C3 established, then C5 comes along and also separates into C5A to become the anaphylactic molecule over here. C5B attaches to C3B and continues the polymerization. We have C6, 7, 8, 9, which add up to our membrane attack complex, and you can see it inserting itself here. It's a transmembrane little sort of device that basically causes the outflow of and the sort of death by 1,000 cuts, as it were. It's going to lyse the infected cell. So that's the job of that. Okay, so we come over here and we discover some things about inflammation, and we talk about fever. And so we have something called pyrogens. That's another molecule of interest. We're supposed to be at 37 degrees Celsius, 98.6, and it's possible to raise the temperature of the body. So in addition to the commonly thought of cardinal signs, in which there is redness and heat, so more than just having blood flow into the area, we can actually activate a pyrogen and change the body temperature. Sometimes these are activated by nutrients. Niacin, again, is something that is, we'll see that in later chapters on nutrition. Niacin can actually give us a little flush and a little heat. Sometimes certain foods can do it for us. Certain meats or fish can cause us to have an increase in temperature. Okay, so that takes care of that pathway right there.